In my last video on lasers, I had put together an infrared detector, and I wanted to show how that circuit's designed and how I bias the transistors. But before we do that, we need to know a couple theorems, Norton's theorem and Thevenin's theorem. And I'll leave that for the actual biasing the transistor for another video. But now, for Norton's theorem, it states that any linear circuit can be simplified into an equivalent circuit with one current source in parallel with a resistor. And Thevenin's theorem states that any linear circuit can be simplified to a single voltage source in series with a resistor. So this is current in parallel with a resistor, and this one is voltage in series with a resistor. Now, over here we have a voltage divider, and this is how I bias the transistor in that project. And we have a 250 ohm resistor here, and we have a 20K resistor down here. And we want to find the voltage between A and B, the current between A and B, and the resistance between A and B. Now, if you're doing this circuit, this 250 ohm resistor, they're not common. I use those because transistors put out 4 to 20 milliamps, and 20 milliamps into 250 ohms gives me 5 volts, and 4 milliamps into 250 ohms gives me 1 volt. So it just makes it easier. So I have ordered these special. Anyway, you can use whatever resistor you have there. Now, Thevenin's theorem states that to find the resistance between A and B, we need to short out the power supply. So we short this out, and that takes the top of R1 and puts it down to the bottom of R2 down here. So that puts these two resistors in parallel. So to find the parallel resistance down here between A and B, we just take R1 times R2 divided by R1 plus R2, and that gives us 246.9 ohms. Okay. Now the voltage is just our 5 volts here times R2 divided by R1 plus R2, and that gives us 4.938 volts. Now to find our current, all we do is we take our resistance, 246.9, and we divide that into our voltage up here, and it gives us 20 milliamps. Okay. So this circuit here should have 4.93 volts here, 20 milliamps, and a resistance of 246.9 ohms. Okay, so let's take a look at. I've got one here. I've got 250 ohm resistor here, and let's see if I can get this in here. And what do we have here? Can you see that? Yeah. So 20 milliamps, a little over 20 milliamps. My voltage might be a hair high on there, but that's working out. The math worked out good on that one. Now, we're going to add a load to this. We're going to put a 120 ohm resistor across here. And when we do that, the voltage is going to stay the same out here. This is open circuit voltage here. And to find our resistance, though, between A and B, we take our R3 here, this one, plus these two in parallel. We short this out again. R1 times R2 divided by R1 plus R2. And so if we add all that up, it gives us 366.9 ohms. And then we take our resistance and divide that into our voltage here, and that should give us 13 milliamps. Okay, so we're going to let me see here. There's the circuit again. This is a 120 ohm resistor, and I put that in there, and let's see what it does. It doesn't do anything. There we go. I think my voltage is a little high. 13.8 volts. 13.8 volts. 13 milliamps. 13.8 milliamps. So that works out pretty good. These resistors this is a 5% one here. And so it looks like the math's working out all right with these theorems here. So that's how we're going to calculate the bias of our transistor next time around. But for now, Thank you.